So we're here, and we're going to be talking about spectral graph theory. And I just want to make a quick pitch. Imagine that you're in an elevator, and you happen to have a whiteboard in the elevator. And someone says, okay, what is spectral graph theory? Can you explain that to me? You say, all right, well, since we only have a few moments while we're in our elevator, let's do our elevator pitch. So we have to start by saying we have these objects called graphs. All right. Now we're going to get into more detail about what graphs are, and I should add that we're not going to make a strong assumption that you know a lot about graphs. You probably have met them before. And when you have met graphs, usually the way you've met them is by pictures. That's the way we visualize graphs. And we have a bunch of circles. We call these vertices or nodes, depending upon where you learned about graph theory. And then we have lines, which we call edges. And as I said, we're going to talk more about graphs as we go on. But if I were to say, what is a graph? What's the point of graphs? And I would say graph theory really cares about connections. The connections between objects, and that's what it studies. And so you have to say, well, what are your objects? And these are our vertices. And they can be anything. They can be very abstract things. They might be elements in a group. They can be very concrete things. They might be people. And then what are the relationships? Well, again, they can be whatever you define them to be. So if we go back to the abstract and talk about elements in a group, you might say, well, group actions take elements from one to another, so we might mark that by an edge. If we go back to our more real-world applications and say, well, I have people. And what do I do with people? Well, they may be friends and not friends, and then we get things going in that direction. So if you stop to think, you say, well, the study of connections seems really important because that covers pretty much everything. Exactly. That's why graph theory is everywhere. It's just a matter of looking for it. Now, I mentioned that, of course, when we oftentimes think about graphs, we think about the pictures, but graphs aren't pictures. And that's just a way to represent them. And you might say, well, what are they? Well, there's technical things. There's a pair of sets and dot, 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 dot. We'll get into that later on. But how do we store? Suppose we were to put it into a computer. What's a reasonable way to store it? Well, a really simple way is to put it into an array. And how does that work? Well, what we do is we have this table of information, and we say we have our vertices, which remember those are our objects, and we have a vertex. Each row is associated with a different vertex, and then each column is associated with a different vertex, and then we have an entry in the table. And the point here is that our entry tells us how the two vertices, u and v, are related. So that's what's going on with this array. I say, okay, great. And the nice thing is arrays are very friendly to computers. Computers love arrays. They love dealing with information. And if I have the graph, I can go to the array. If I have the array, I can get back to the graph, at least for most kinds of arrays we can. So we say, all right, great. And that might be the end of the story. But then along comes linear algebra people. And they say, don't call this an array. Call it a matrix. And people are like, okay, potato, potato, sure, why not? We'll call it a matrix. Because for a lot of people, when they think of a matrix, it's just a bunch of numbers. But actually, it's more than that. You see, a matrix is an array with benefits. All right, so what kind of benefits do we have? Well, in particular, once I start talking about a matrix, I can start talking about things associated with a matrix, and we'll call that the spectra. If you like, what is the spectra? Well, it's a bunch of numbers, lambda 1, lambda 2, all the way down to lambda n. And so these are what we call the eigenvalues. And we'll talk a little bit about what these are in a moment. just as a refresher, we have that. Okay, so that's our basic underlying picture. We have our graphs, we can associate with a matrix, and a matrix we can associate with a spectrum. Now, if you look at our arrows, you'll notice that between graph and matrix, it's a two-way street. If we have one, we have the other. But between matrix and spectra, it's not. Well, why is that? Well, spectra, when you have these numbers, these eigenvalues, it captures a part of the information about the matrix and what the matrix represents. But it doesn't capture everything. And so my PhD advisor, in her book, Spectral Graph Theory, she likes to relate this to the spectrum of light. So, for instance, you can look at a star and say, well, is this star a hydrogen star or a helium star? Now, we can't go and actually go to the star and pick up a sample and check, but what we can do is we can look at the light, the spectrum, and see the behavior of it, and that helps us understand the composition. And in the same way, what we're going to see is that the spectrum associated with the matrix gives us some information, but maybe not all. And so our class is essentially this arrow right here. This is spectral graph theory. The goal is to say, how much can we figure out knowing just the spectrum about the graph and about the structure? So there's a song by the Rolling Stones that has the lyrics, you can't always get what you want. No, you can't always get what you want. But if you try real hard, then you just might find you get what you need. Now, they said it much better because they can sing, but the moral here is, we can't get everything. And we'll see explicit examples of that. We'll see that there are examples of graphs where if we only look at the spectrum, are indistinguishable, though the graphs themselves are clearly distinct. At the same time, we'll see that there's information we can say, oh, I might be able to say how many edges there are, how many components there are, how quickly information can propagate in a network. There's various things that we can see. And so, depending on what we have. Now, one thing I'll mention now, and we'll come back to as we go on, is this matrix here, I've been a little bit vague. Because I say, well, you can associate with a matrix. And the word is important here. It is not the matrix. Because there's lots of different ways we can think about what kind of information we're putting inside of here. So it's how U and V are connected, but you might say, well, maybe U and V, I'm looking at adjacent or not adjacent. Or maybe I'm looking at what's the distance. Or maybe I'm looking at how likely am I to transition from one to another in a random process. So there's different possibilities. And so each possibility gives us a different matrix. And that means that, of course, we have lots of things to explore. Now you might say, well, is there a best matrix? And having been a student of Fan Chung, I have to say I'm contractually obligated that the normalized Laplacian, which of course we won't get into what that means explicitly for a long time, is the best. But the truth is that there's not really a best matrix. And there's no sort of, this matrix is the one matrix to rule them all. There's no such matrix. It's just every matrix has positives, every matrix has negatives. And usually you look for ones with lots of positives and relatively few negatives for what application you have in mind. All right, so that was a very long elevator ride, but that is what spectral graph theory is about. So, where are we going to start? I'm going to start with a little bit of just a reminder of what we mean by spectra. So a little bit of linear algebra review. We'll probably at some point get into what are graphs. So a little bit of graph theory review either today or maybe next time. And so possibly by the end of the first week, we might even talk about what matrix we might look at first. And so, all right. Any questions before we go on? Okay, good. So now you sort of know where we're going. That's nice. All right. So let's remind ourselves a little bit about what we're talking about when we talk about spectra. So a short stroll through linear algebra. And we're going to actually be coming back and forth to linear algebra all throughout our class. And oftentimes what happens is we say, well, what's the right idea? And in particular, we can take, here's a linear algebra result. How do we turn it into a graph theory result? And so sometimes it's obvious and sometimes it's less obvious, but we'll keep coming back and forth. So as we start our short stroll through linear algebra, our basic starting point is we start with the notion of a vector space. So linear algebra, well, you have a vector space. Now, what is a vector space? A vector space is really a place where you have vectors. And of course, what can you do with vectors? There's three key things. One is you can add vectors. Two is you can scale vectors. And three, it makes sense. And so when I say you can add vectors, that means I can take two vectors, I can combine them together to make a new vector. When I talk about scaling, I can take a vector and somehow affect its length, whatever that means. And when I say it makes sense, well, that just means it behaves like you would hope it would behave. So, for example, we can say something like, well, suppose I have the scaling numbers are a and b, and I times it by a vector u, and we'll put a little arrow on top of the vector to help us remember that it's a vector. What should this equal if everything made sense? Yeah, a times u plus b times u. And that's pretty much it. So if you actually sit down and look at like the list of like what makes up a vector space, you'll see most of the requirements are like, yeah, that should make sense. As long as you want it to add and scale, what do you need to throw in there for it to make sense? Now, vector spaces by themselves are not very exciting because there's not really much you can say about them. You more or less say, what do they consist of? You can talk about one object that's important is you have what's known as a basis of a vector space. Now, what's that? Well, these are a collection of vectors. So any vector has a unique, and uniqueness is the important part about a basis, way to write as a combination of our basis vectors. Okay, so that's our vector space. Now we can do a very simple example. We'll try not to be too trivial, so we'll go up one level. Suppose we say that our vector space is the plane. So we'll do R2. And so we can write our vectors as just pairs. So U looks like A and B. All right. Well, so the first question we might have is, do we have a basis for the plane? Does anybody know one? All right. Does anyone know a second one? All right. What's the second basis that we can use? You probably think, wait, which one's the first one? Well, there's... Sorry, what?
I don't know, like, rotate 90 degrees.
Oh, okay. Well, I think you were doing 45 degrees. I like that. A 45-degree rotation. 1, 1, 1, -1. Yeah, 90 degrees pretty much just more or less get you back to the same basis as you did before. But of course,
Technically different.
technically they are. That's true. That's true. But of course, the claim is this is a basis. Okay, so someone give us a vector in R2.
4, 2.
4, 2. All right. So can we write 4, 2 as a combination? Now, of course, when we talk about a combination, I should have added the words linear, because, this is linear algebra, and linear basically means you scale and you add. And so when you talk about things like the derivative is linear, it means, oh yeah, it behaves nicely with scaling and adding. That's what it means. All right, so 4, 2. Does anyone see a nice way for us to write 4, 2 as a combination of 1, 1 and 1 minus 1? So you said, okay, so 3 times the first, and 1 times the second, and all right, so you get 3 plus 1 is 4, 3 minus 1 is 2. Aha, nice. Aha, success. Okay, good. All right, and this is about as far as we get when we just talk about just vector spaces. So where does the fun stuff come? The fun stuff comes from saying, hey, you know what? One vector space is not that exciting, but 2. So what we can do is we can go from one vector space and think about mapping to another vector space. So that's when things start really getting interesting in terms of linear algebra. That's what we care about, is essentially mapping from one vector space to another vector space. Now, when I talk about this map T, I mean, we usually have this underlying assumption that it's linear. So in other words, it respects addition and it respects scaling. So that is to say, if I have T times AU plus B times V, so this is my input, then this is the same as A T times U plus B T times V. So that's what we mean when we say we have things which are linear. All right. Well, the nice thing is we say, oh, this looks like linear combinations of things. And we know, we have this nice idea here that says the basis, everything can be a linear combination of things from our basis. And the great aha says, great. If I want to understand what's happening with the map, all I have to know is what happens with the basis. Okay, good. And so, say, all right, what does happen with the basis? Well, so now we have to sort of talk about various things. So this is when it gets confusing, and you have alphabet soup coming into play. So, well, all right, let's suppose we'll write our basis over here as V1 up to Vn. And over here, we'll write this basis as U1 up to U sub m. They don't have to be the same dimension. There's nothing that requires that your vector spaces have the same dimension. And what's true? Well, if I have T applied to W, well, what do I really need to do? I just have to say, look, instead of figuring out what works for every W, I can figure out what happens to each U. So the aha, what happens to our U1 up to UM? And by the way, if this does not seem like the linear algebra you're used to, don't worry about it. This is going to get swept under the rug very quickly. I just want to say this is the background, the underlying idea, and to say, okay, we want some basics, and we want to make sure we understand where the basics come from, so that the ideas that we do need, we can grab them when we do. All right. So now I say, well, look, if I just want to know an arbitrary vector, I just need to know what happens to a basis. And so what do? Well, we say, look, the basis maps to something inside of V. Well, how do I know that a basis element is going to map to something inside of V?
Because everything maps to something inside of V.
Yes, because everything maps to something inside of V. That's what it means to map. It has to go someplace. I'm not claiming at all that we hit everything in V. That's not the claim. But just everything that I start with has to go someplace. And so I said, well, since it goes someplace, it's going to go to some combination of the basis in V. So it goes to A1, V1 up to some AN, Vn. And so what's our nice aha? Well, we really say, look, what really matters is these coefficients showing up. So somehow T times this first basis element, I'll associate with the list of numbers, A1 up through AN. All right, now we're almost to our point here where we say, well, how do we get to a matrix? Okay, so here's the matrix part of it. So now what we'll do is we're going to construct a matrix, and by the following rule. So we're going to have, and I really should have prepared better here, because I can see I'm going to get lost in my subscripts and various things. And so what I want to think of is, all right. The way we make our table is we do it a column at a time. Channel our inner Lord of the Rings character. Column, 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 right? Yes? Right. So we do a column at a time. And so when I look at this ith column, what I'm going to think of it is this is associated with u sub I. So the ith column is associated with the vector u sub I. And now what we're going to do is we're going to fill up that column with these entries. So if this is, all right, so we'll make this a u sub I. So this would be the A1 down to AN associated with that particular option. All right. Well, and you repeat, repeat, repeat. The claim here is that this does what we claim it does. Now, you might say, well, wait, what do you mean by it does what we claim it does? Well, what we can think of is our inputs. I'm going to think of u sub I. I'll write it as a nice 0, 1 vector, where it's almost all zeros except in one spot, namely in the ith spot, and that spot will be a 1. And now, what do I want? Well, I want to say what happens when I map u sub I by this transform. Well, I want to somehow pull out these coefficients. And if you're familiar with matrix multiplication, then you'll see if I put a 0, 0, 0, 1, 0, 0, 0, I'm doing exactly that. All right. And so in general, and now I've run out of space, so that's all right. We have more paper. Paper is a renewable resource. It grows on trees, so we can continue to write on more paper. And so the big punchline here is that when we look at what we're applying, so if I have a vector, and I see it's been too long since I've taught linear algebra because I'm rambling a little bit more than I normally do. I ramble a lot, by the way, if you haven't picked up on that. I'm very good at that. I'm very good at going off on tangents, too. That's because I've done too much calculus. And but okay, so the moral here is when I'm thinking of applying t to a vector, and I'll call it c1 down to cm. Well, really what this is representing here is this is saying, well, c1, u1, c2, u2, all the way to cm, u sub m. That's That's what we really mean when we are representing this column here. It's our basis. We've made a choice. And then we apply each one. So because it's linear, we can push it through. So C1 times T U sub 1, C2 T U sub 2, and so forth and so on. And now we say, well, great. Each one of these is associated with its column. So that becomes C1, and we'll add an extra subscript here. So A11 down to N1. So that's where U1 maps. C2 will be A12 down to N2. That's where U2 maps all the way across and till we get to our end. And then you say, well, all right, so that's what happens. It's this linear combination of vectors. And now, if you're familiar with, as I said, multiplication, you can combine all these vectors into a single nice array, and the matrix, if you will. And you'll see, lo and behold, this is what we normally write in this fashion. C1, C2, down to Cm. So that when we talk about matrix multiplication, matrix times vector, you say, well, really, you scale the first vector by this value C1, scale the second value vector by C2, and so forth and so on. So that what you have is a linear combination of the vectors, which is what we should have. All right, so that's our basic idea. Okay, so let's see. What do we need to talk about? Well, in our last few minutes, we should talk about what is an eigenvector then. In our closing stage in day one, what is an eigenvector in this setting?
Are you asking us?
Yes, I am. I'm sorry, I don't mean to, I didn't mean for it to be too rhetorical.
A vector that gets matched to a multiple itself.
Okay, so why do we care about such vectors? And why do we call them eigenvectors, by the way?
Eigen means
German.
Yeah, it's like self or same. I think it's German.
Yeah.
And I don't know if you have to be like, not everybody is upset when they speak German, by the way. You know, it's just in World War II movies where it's like the Germans are always upset, and so sometimes they're very eloquent. Okay, so yeah, so it's a self vector, and so the eigenvector says, aha. Now this, I should say, is a special case when what you have is the map is from the space back to itself. So we're mapping from one vector space back onto itself. So that's our setting. And in this case, an eigenvector is something where the map is very simple. So in other words, if I apply the linear map to our vector v, this will come back as some multiple of the vector v. All right, good. And so the vector, this is our eigenvector, and it has to obey this. Any constraints that we put on our vector?
non-zero.
V can't be 0. Well, why? Because zeros are very non-interesting. As I like to tell my engineering students, the 0 vector is the art history major of vectors. It's directionless, has nowhere to go. Now I can tell this joke at Iowa State because there are no art history majors, and so I'm not offending anybody on campus. So I can't tell this joke at University of Iowa. So I'm just going on the record in case somebody, reports this video to YouTube for being like, Steve has hate speech. No. I love people. Okay, so V is not the 0 vector. What, by the way, is the 0 vector? We said it can't be the 0 vector. So what is the zero vector?
The vector that's all zeros.
Okay, the vector that's all zeros. Oh, additive identity. Very fancy. I love that terminology. Okay, so if we think of vectors as agents of change, you know, that sounds like a very fancy buzzword you might hear. Be an agent of change. So if we think of a vector in that way, then the vector represents how much things are changing. So for the zero vector, how much do things change? Yeah, it's the vector where nothing changes. And so that's the zero vector. Now the reason we don't really care about the zero vector is because if I apply the zero vector and plug it into my transformation, what needs to come out? It has to be the zero vector. Why does it have to be the zero vector? Yes, because otherwise it doesn't make sense. It's the correct answer. Because if it wasn't the zero vector, then of course if I scale 2 times the zero vector, and if it wasn't the zero, then I'd be getting all sorts of weird things happening, you know. So yes. All right, good. So then lambda, we call this an eigenvalue. Now, one thing that we should point out here, and this comes into play as we go along, is that this matrix that we look at, this is basis dependent. If you change your basis, then you change your matrix. Now, sometimes you like that flexibility and sometimes you don't. But what about eigenvalues and eigenvectors? Are those basis dependent?
They should not.
Yes, they should theoretically not be, and they aren't. They do not depend on the basis, and so that's why we like them, is that they're somehow inherent to the linear transform itself. It's something which is static. And so what we can look at is we can say, well, what can we say about these eigenvalues? What can we say about these eigenvectors? So that's something, an inherent property of T, the linear transformation, not the matrix. And so that gives us a way to sort of tell, are 2 linear transformations distinct? So there's a way of separation. I can say, aha, this linear transformation is not that linear transformation because these eigenvalues are not those eigenvalues. More subtle is, are things the same? Well, that gets more complicated. But the good news is that for us, and we'll get into this at the start of next week, is that we tend to focus on linear transformations which are nice. And in particular, spoiler alert for next week, is that the kind of transformations we care about have the property that their matrices are symmetric. And what's nice about matrices which are symmetric?
A lot of things.
There are, yeah, a lot of things are, in particular about eigenvalues. What's nice about the eigenvalues when the matrices are symmetric?
It's diagonalizable, so it's
Diagonalizable? Yeah, okay.
so
All right.
it's enough eigenvectors.
Right?
It's eigenvalues are real. Sorry.
Yeah, the eigenvalues are real. That's what I was hoping someone would say. That's right. We're going to be keeping it real. This semester we're about keeping it real. So it's going to be a good time. All right, and looking at our time, I think this is a good place for us to stop. And next time we will jump into graphs. So now that we've said, aha, we have this underlying idea of linear transformations, and that's what the spectra is. The spectra are these eigenvalues, these lambdas. Next time we'll talk about what are graphs, and then next week we'll say, wait, are these things really related? I'm less convinced now after listening to these 2 different ideas, but they are in fact related. So, all right, have a good day.